Okay, thank you very much for attending. I'd like to acknowledge my co-authors, the PhD student Mingyang Liu, who's in Beijing now and could not make the trip, and Professor Wei Shi also. I'm from Laval University, that's the UL at the bottom, and this work was done onto the Center for Optics, Photonics, and Lasers. So I'll start by giving you some motivation and challenges for the work I guess I should have read the title, I'm sorry. This is on silicon photonics to add 5G radio over fiber services to passive optical networks employing carrier reuse. So I'll tell you about why we want to do this overlay of radio over fiber onto passive optical networks. And I'll tell you why this is challenging, and then we'll go into the solutions that we're proposing, in particular transceivers for the passive optical network using silicon photonics. I'll show you our experimental setup, show you our results, and a little bit of discussion on where we would like to go with this. So we're looking at the use of radio over fiber. So one way of doing radio over fiber is to use digital radio over fiber, and that uses the CPRI standard. Unfortunately, the CPRI standard is very demanding in terms of bandwidth. It does a very large expansion of the required bandwidth, and so we'll be considering analog radio over fiber instead. Now, we're looking at passive optical networks as a way to give a supplementary source of 5G small cells. So the idea is that you already have deployed fiber, and to use this to reduce your CapEx expenses by being able to exploit it in two ways. And the idea is it would actually, as I mentioned, piggyback on top of fiber to the home infrastructure. So you essentially are getting a network of dense femtocells created on your deployed passive optical network fiber. Of course, you already have a 5G network, but this is a way to augment that with added capacity. So if I look at the architecture that we have in mind for these passive optical networks, we're assuming, when I say next generation PON, I simply mean that there would be perhaps a wavelength division multiplexing option. And the idea is that we would, at the remote node, we would intercept the fiber to the home signal, and at that point we would put in basically something like a baseband hotel there that would be able to add the 5G services at that point. So what are the challenges in trying to add this radio over fiber onto a passive optical network? Well, there are a few. First of all, passive optical networks are single feeder networks, so you have to have both uplink and downlink on the same fiber. You also, very important to have colorless operation. What we mean by that is you have to avoid tunable optical sources at the customer premises, at the ONU. Ideally, you would maybe want to avoid any ONU optical source. And all of this, the motivation is to keep the costs down in the PON. Well, the way of achieving this, of avoiding sources at the ONU, is to use a distributed carrier or to reuse the downlink carrier that is delivering your fiber to the home service. If you do this, that means you have to deal with a weaker uplink signal. So this is one of the challenges. And of course, we have coexistence issues. The idea is this infrastructure exists for the fiber to the home digital broadband signal, and we want to add on to that the radio over fiber. So I'm particularly investigating silicon photonics solutions for this application, and silicon photonics has an indirect bandgap semiconductor material which is inefficient in generating and detecting light, but is very low optical loss, which means it's excellent for making switches, filters, waveguides, etc. And of course, most importantly, it's compatible with mature CMOS technology, which means we can highly integrate with low cost. So if I look, why silicon photonics in this application, I look at passive optical networks and I say, well, I'm going to reuse my carrier anyway. So the fact that silicon photonics cannot provide a source doesn't really bother me. And all the other functions that we need are well covered by silicon photonics. And of course, the compatibility with CMOS just means that the price will be lower, which is very important in a PON application. And of course, why am I doing new research in this? It's because a lot of the current silicon photonics transceiver solutions, well, there are a lot of coherent transceivers that are gathering attention, and nothing for this particular radio over fiber application has been investigated. Of course, I could look at indium phosphide, but then I would lose all the advantages of silicon photonics that I've already mentioned. So, going back to the architecture I proposed, first of all, I'm going to assume that the smart edge is in place, and that I have, for a particular wideband WDM slot, I have in red this broadband signal, and in the blue and green, there's some 5G signals which are being added inside of this WDM slot. Now, assuming that that's in place, what I'm talking about in this paper is what do you do at the ONU? So we've had some other work that discusses what to do at the smart edge, but today I'm talking about this 5G ONU solution. So what do we need to do? We need to detect the radio over fiber signal. We need to detect the broadband signal, and then we have to remodulate the radio over fiber to go back on the uplink signal. So here's the subsystem design in silicon photonics, and you can see I have here the radio over fiber detection, the RoF signal detection first. So coming in, I have this red broadband signal, this blue radio over fiber signal, and the distributed carrier that's coming with this PON signal. First thing I'll do is I'll filter and drop the radio over fiber. Then I'll have to drop the OFDM signal, and then finally I'll remodulate onto the residual carrier for the uplink. And the way that we've chosen to do this is using cascaded microring resonators. So this choice was used because they're very compact and they have natural routing functions already. We have a drop and a through port, which makes it very easy to implement this structure of stripping off one signal after the other, and finally leaving the carrier for remodulation. Of course, ring modulators also have very small footprint, low loss, and low power consumption, which is excellent for this application. So the footprint, here we have the mask layout below the sketch of the spectrum, and we can see here the first set of microring resonators, which will be used to strip off the radio over fiber signal. Whoops. Getting ahead of myself. The second set of microring resonators here, and then the photodiodes to do the detection of those two signals, and finally the microring modulator, which is for the uplink carrier remodulation. So these are very small, and I just want to show you the entire layout. Of course, we have very big pads, which we are using just to do the probing, but the actual size of the components, the microring resonators, is very small. This is a photograph of the chip that we use in our experiments. We have it optically packaged, so I think you can just barely see up here in the corner. The low frequency or DC connections for thermal tuning were wire bonded, and then here we have an RF probe, which is where we're doing our remodulation. We're putting our RF signal onto the uplink. So this is our experimental setup. We start with our chip, which has got the microring resonators and the microring modulator and the photodetectors. And of course, there's thermal tuning that we're doing off the chip. Of course, thermal tuning would be used to choose the WDM channel that we want to capture. And fine tuning could be used for other purposes, as I'll be explaining. So off chip, we do our generation of the signal, and in our case, we'll be using a OFDM broadband signal and a 2.4 gigahertz carrier for the 5G narrowband signal. We do the detection using a real-time oscilloscope, so we capture the signals and then offline process it to do the verification that we successfully recover our radio over fiber signal and our OFDM signal. Then we have off chip, we generate our RF, our radio over fiber signal for the uplink, and then again with the RTO test the performance of that system. So here I'll show you the spectra that we are examining. So we'll start with, as we're just going into the chip, we can see three contributions. We have the OFDM, the radio over fiber, and the carrier. So here is the broadband OFDM signal. Here we have actually 5 radio over fiber carriers roughly around 2.4 gigahertz. And this is the main distributed carrier in the PON system. So the first step is to do radio over fiber detection. And here in yellow, you can sort of see the passband of this microring resonator, where we're going to selectively, I said we would do some fine-tuning on the thermal tuning. And that allows us to change the shape of the filter and the position of the filter. And it allows us to play with how much of the carrier is dropped for reception. Of course, the stronger the carrier is, the better the reception, but I have a power budget that I have to respect. Now, if I go past that first microring resonator, first of all, here in the inset, I'm showing you that I've used 4 dB of my power budget in order to do reception of that radio over fiber signal. Now I'm looking at the red trace in this spectrum, and of course the broadband signal has been attenuated to some extent by the tail of the first microring resonator, but again, this is tunable. And you can see that the radio over fiber signal has been very strongly suppressed, so that when I go in to do detection of the OFDM signal, it's providing very little interference. And when I go past that second one, we can see now that I have used 2 dB of the power budget in order to do detection of the OFDM signal. So after going through these 2 stages of microring, cascaded microring resonators, we can see that the OFDM signal very strongly suppressed the RoF, and what remains is a very clean carrier. Very powerful because I've only leached off about 6 dB for my detection. So I have very good power budget. We have over 20 dB suppression, in fact, of the downlink signal. So the last part of this demonstration is the remodulation, to take that cleaned carrier and remodulate it with the microring modulator. And the microring modulator we use has a PIN structure. It can have very high modulation depth and low swing voltage, desirable characteristics. And one downside would be a limited bandwidth. However, this application is for a radio signal, which is by its nature narrowband, so that's really not a concern. In this case, we forward bias the microring modulator at 0.85 volts. So this is the remodulated signal. We can see that the residual downlink OFDM signal is very, very small. You can just make out here the residual radio over fiber signal from the downlink, and we can see that it's about 30 dB down from the remodulated signal. Okay, and as I mentioned, we have sort of this natural suppression that is coming through from the microring modulator's intrinsic wavelength selective properties. I want to mention just in particular that if we look at what we chose to examine, we have in red here, these were the downlink radio over fiber signal. I said we had 5 of them, 5 narrowband signals. And when we remodulated, we deliberately put 2, and we put one in sort of in between where there was no downlink signal, and we put another one right on top of the downlink so that we could compare the effectiveness of our suppression before remodulation. And both channels had bit error rate that was well below the effect threshold, so that the suppression was more than adequate for the application. So in conclusion, I've shown you a PON architecture which could support heterogeneous services. It's compatible with WDM PONs. We examined one 50 gigahertz slot in this demonstration. It's compatible with broadband digital downlink. In this case, we used a 16 gigabit per second OFDM signal for our demonstration. And we had multiple radio over fiber signals on the downlink. This demonstration was 2.4 gigahertz. It could also be at 28 gigahertz and still fit in the slot that we're proposing. I demonstrated a silicon photonics solution, so we designed, characterized, and then put into a system test our ONU silicon photonics solution. We demonstrated that we had good power efficiency, that we were compatible with colorless operation. We had good coexistence, which means good reception of all signals, and the uplink radio over fiber modulation. The suppression was adequate and, in fact, more than adequate for that. So I thank you for your attention.